September 19th, 1944, Lorraine, France. A Panzer IV Ausf H sits motionless beside a muddy road, 3 kilometers behind the German defensive line. Oberfeldwebel Kurt Schneider stands beside the disabled tank, a maintenance manual open in his hands. The problem is simple: a broken torsion bar on the third road wheel. The solution should be equally simple: replace the bar, resume operations. Preparing and narrating this type of story took us long efforts and hard work. So if you are enjoying the story, please consider subscribing to our channel. But there are no replacement torsion bars. Not in the battalion supply dump, not in the regimental depot, not within 50 kilometers. The part must be ordered from Germany, machined to specification, transported through Allied air interdiction, and delivered to a front that moves 10 kilometers eastward every day. Estimated time, 3 weeks, if it arrives at all. 400 meters down that same road, an M4A1 Sherman from the American 4th Armored Division sits with its own problem. The final drive housing is cracked. Transmission fluid leaks onto the road in a dark puddle. The crew expects a similar fate. Abandon the vehicle, wait for a factory replacement, weeks of delay. Instead, the battalion maintenance sergeant arrives with a cutting torch, a welding rig, and a replacement final drive cannibalized from a knocked-out Sherman recovered 2 days earlier. 6 hours later, the Sherman is moving again. Schneider watches the American tank rumble past his position and feels something he has felt increasingly often since the Normandy breakout. Not fear, not even anger, comprehension. The Germans built a better tank. The Panzer IV's 75mm K40L48 gun outranges the Sherman's M3 by nearly 300 meters. Its frontal armor, 80mm on late models, is thicker. Its suspension is more sophisticated. By every technical measure, the Panzer IV is superior, yet the Americans are winning. And Schneider suddenly understands why. It is not about which tank is better. It is about which tank is still moving after 4,000 miles. This is a story about two philosophies of war. One built machines for technical perfection. The other built machines for logistical reality. One designed tanks that could outshoot anything they encountered. The other designed tanks that could be repaired in a field with a wrench and a welding torch. The Panzer IV was arguably the better fighting vehicle, but the Sherman was the better weapon of war. And the difference between those two things decided the outcome in Western Europe. When we speak of tank superiority in World War II, we instinctively think of armor, thickness, gun penetration, speed, maneuverability. All valid metrics in a controlled comparison. But war is not a controlled comparison. War is 4,000 miles of roads, each mile wearing on tracks, transmissions, engines, suspensions. War is supply lines, stretched across oceans and continents. War is maintenance performed not in factory workshops, but in muddy fields under artillery fire. War is replacement parts that may or may not arrive before the front moves again. In this context, which tank is superior? The question becomes more complex. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 1933. Germany begins rearmament in violation of the Versailles Treaty. The Wehrmacht needs tanks, medium tanks specifically, capable of breakthrough operations and sustained combat against peer adversaries. The initial design contracts go to several firms: Krupp, Rheinmetall, MAN. The specification calls for a tank weighing approximately 20 tons, mounting a gun capable of defeating contemporary French and Soviet armor with a crew of 5. The Panzer IV emerges from this requirement. Designed by Krupp under the designation Versuchskraftfahrzeug 622. Experimental Motor Vehicle 622. The VK620 begins testing in 1936. The first production models, designated Panzer Kampfwagen IV Ausf A, roll off assembly lines in October 1937. Initial specifications: weight 17 3/10 tons, armament 75mm KWK 37L24, a short-barreled gun designed primarily for high-explosive fire against infantry and fortifications. Hull armour, front 14.5 mm, later increased to 30 mm in the Ausf B. Sides, 20 mm. Engine, Maybach HL 108TR, developing 250 horsepower. Maximum speed, approximately 31 km per hour on roads. The design philosophy is distinctly German: precision engineering, tight manufacturing tolerances, components machined to exacting specifications. The transmission is a sophisticated 6-speed synchro mesh unit, the ZF SSG 76, more complex than necessary, but smooth and efficient. The suspension uses leaf springs mounted externally on the hull, an unusual configuration that provides excellent ride quality but complicates field repair. Each road wheel is individually sprung, 8 wheels per side, overlapping slightly. The torsion bar suspension used on later German tanks has not yet been adopted for the Panzer IV. The overlapping wheel arrangement, called Schachtelaufwerk in German, distributes weight efficiently and provides a stable firing platform. It also means that to replace an inner road wheel, the outer wheels must first be removed, a maintenance headache. The Maybach engine is a masterpiece of German automotive engineering, 12 cylinders in a 60-degree V configuration, aluminum block, overhead valves. Smooth, powerful, reliable when properly maintained, but it requires high-grade lubricants, precise valve adjustments, and careful tuning. This is not a tractor engine, this is a precision instrument. From 1937 to 1940, the Panzer IV undergoes continuous refinement. Ausf B increases armour, Ausf C improves the transmission, Ausf D adds a new engine, the Maybach HL 120 TRM, developing 300 horsepower. Ausf E strengthens the hull to accommodate heavier armour loads anticipated for future variants. Each modification improves the vehicle. Each also increases complexity. By May 1940, when Germany invades France, the Wehrmacht fields approximately 280 Panzer IVs of various marks. They perform well. The short 75 mm gun is effective against French infantry positions and light fortifications. The armour, though thin by later standards, is adequate against French anti-tank guns of the period. But the Panzer IV is not yet the tank it will become. That transformation begins in the Soviet Union. June 22, 1941. Operation Barbarossa. Panzer divisions cross into Soviet territory expecting to encounter outdated T-26 and BT series light tanks, relics of the 1930s, easy prey for German guns. Instead, they meet the T-34. The T-34 is a revelation. Sloped armour that deflects German shells. A long 76 mm gun that can penetrate Panzer IV frontal armour at ranges exceeding 1,000 metres. Wide tracks that provide excellent mobility in mud and snow, and it is produced in staggering numbers. The Soviet Union will eventually build over 84,000 T-34 seconds, more than all German tank production combined. The Panzer IV's short 75 mm gun cannot reliably penetrate a T-34's frontal armour beyond approximately 300 metres. German crews are forced into close-range engagements where Soviet numerical superiority becomes decisive. The reports from the Eastern Front are alarming. The Wehrmacht needs a better gun. Fast. In March 1942, the Panzer IV Ausf F2, later redesignated Ausf G, enters production. The critical change is Plies, armament. The short KK-37L-24 is replaced by the long KK-40L-43, a 75 mm gun with a barrel length of 43 calibers, muzzle velocity approximately 740 meters per second. At 500 meters, it can penetrate approximately 91 millimeters of vertical armor. Now the Panzer IV can engage T-34 seconds at combat ranges. The psychological impact on German crews is immediate. They are no longer helpless. The Panzer IV, initially designed as an infantry support vehicle, has become a tank destroyer. Further improvements follow rapidly. The AUSF-G increases frontal armor to 50 mm plus 30 mm of applique plating in critical areas. Total frontal protection, 80 mm. The AUSF-H, introduced in April 1943, replaces the leaf spring suspension with torsion bars and updates the transmission to the SSG-77. It also mounts an even longer gun, the KOK-40L48, with a barrel length of 48 calibers, and improved penetration. Weight climbs to 25 tons. The Maybach HL120 engine, still rated at 300 horsepower, is now pushing significantly more mass. Power-to-weight ratio drops from approximately 15 horsepower per ton in the AUSF-A to 12 horsepower per ton in the AUSF-H. Maximum speed decreases. Acceleration suffers. Fuel consumption increases. But firepower and protection improve. It is the classic tank design trade-off. By late 1943, the Panzer IV is a formidable combat vehicle. In a direct engagement at medium range, it can trade shots with a Sherman and frequently win. The KUK 40L48 outranges the Sherman's 75mm M3. German optics are superior. German crews, by this point in the war, are highly experienced. Yet the Wehrmacht is losing the war. Why? The answer lies not in what happens during combat, but in what happens between combats. The 4,000 miles that wear down every mechanical system. The supply chains that must deliver parts across a continent under constant air attack. The maintenance procedures that must be performed not in factory conditions, but in field conditions by exhausted crews with limited tools. Here, the Panzer IV's precision engineering becomes a liability. 1943. Tunisia, the same theatre where American forces first encounter the Stug 3 inches devastating ambushes. Here, they also encounter the Panzer IV in large numbers. The Africa Corps fields approximately 120 Panzer IVs during the Tunisia campaign. By May 19, 1943, when German forces surrender, the Americans capture dozens of intact or repairable Panzer IVs. They ship several back to the United States for detailed evaluation. Aberdeen Proving Ground, Maryland. Summer 1943. American engineers perform the same exhaustive analysis on the Panzer IV that they will later perform on the Stug 3. They measure, they test, they compare. The findings are documented in a classified report, Technical Intelligence Report, Panzerkampfwagen IV AUSF-G. Armor protection. The Panzer IV AUSF-G's frontal hull is 50 mm at 0 degrees vertical, with an additional 30 mm of applique armor bolted on in critical areas. Effective frontal protection, approximately 80 mm. The M4A1 Sherman's glacis is 51 mm at 56 degrees, giving an effective thickness of approximately 76 mm against kinetic penetrators. On paper, the advantage goes to the Panzer IV. In live-fire testing, American 75mm M61 armor-piercing rounds penetrate the Panzer IV's flat frontal plate at ranges up to 1,000 yards. The Sherman's sloped glacis, despite being slightly thinner, proves more resistant. Angled armor is more effective than flat armor of equivalent thickness. Firepower. The Panzer IV's KWK 40L48 delivers superior performance. Muzzle velocity approximately 790 meters per second versus 619 meters per second for the Sherman's M3 gun. At 1,000 yards, the German gun can penetrate approximately 89 millimeters of vertical armor. The American gun, approximately 68 millimeters. The German gun can reliably penetrate a Sherman's frontal armor at ranges where the Sherman cannot return effective fire. Mobility. Maximum speed on roads, Panzer IV approximately 38 km per hour, Sherman approximately 42 km per hour, cross-country speed, Panzer IV approximately 15 to 18 km per hour depending on terrain, Sherman approximately 20 to 25 km per hour. The Sherman's wider tracks, 421 mm versus 380 mm, provide better flotation in soft soil. The testing officers note this with interest. The German tank has the better gun, but the American tank is faster and more mobile across varied terrain. Then comes the maintenance evaluation. And here, the American engineers discover something remarkable. November 1943, Aberdeen Proving Ground, Maintenance Trial. The task is simple. Perform routine field maintenance on both vehicles under simulated combat conditions. Limited tools, no specialized equipment, time pressure. Task 1. Replace a broken track link. Both tanks throw a track during cross-country runs. A common occurrence. The crew must repair it and resume movement. Sherman crew. The track is held together with a single steel pin per link, called an end connector. The pin is secured with a wedge bolt that can be driven out with a hammer and drift punch. Tools required: hammer, drift punch, track jack. The crew jacks up the suspension, removes the damaged link, inserts a spare from the onboard stowage, drives in the pin, secures the wedge bolt. Time elapsed, 28 minutes. Panzer IV crew. The track uses a more complex pin and bolt assembly. The crew must first loosen the tension on the track using the idler wheel adjustment mechanism. Then remove the securing bolts, extract the pin, remove the damaged link, install the replacement, reinsert the pin, install new securing bolts, and retension the track. Tools required: several specific wrenches, hammer, drift punch, track jack. Time elapsed, 53 minutes. The American observers note this carefully. The Sherman's simpler track design allows faster field repair. Task 2. Replace a road wheel. Both vehicles suffer damaged road wheels from mine strikes. Sherman crew. The Sherman uses a vertical volute spring suspension, VVSS. 3 bogies per side, 2 road wheels per bogie. The road wheels are mounted on a simple stub axle. To replace a damaged wheel, remove the hubcap, remove the retaining nut, pull off the wheel, install replacement, reinstall nut and cap. Tools required: large wrench, hammer. Time elapsed, 19 minutes. Panzer IV crew. The Panzer IV uses 8 overlapping road wheels per side in the Schachtelaufwerk arrangement. The damaged wheel is an inner wheel, 4th from the front. To access it, the crew must first remove the 3 outer wheels ahead of it. Each wheel is secured by multiple bolts. After replacing the damaged wheel, the 3 outer wheels must be reinstalled. Tools required: multiple wrenches, jack, blocking. Time elapsed, 2 hours and 47 minutes. 2 hours and 47 minutes to replace a single road wheel. The American observers are stunned. Major George Thompson, Chief Test Officer, writes in his evaluation, "The German suspension provides excellent ride quality and weight distribution. However, the overlapping wheel design creates severe maintenance penalties. In combat conditions, a tank with a damaged road wheel requiring 2+ hours to repair is effectively a battlefield loss." Task 3. Engine replacement. Both vehicles suffer catastrophic engine failures during extended high-power runs, a realistic scenario. Engines wear out. In prolonged campaigns, they must be replaced in the field. Sherman crew. The M4A1 mounts the Continental R975 radial engine. The engine compartment is accessed through large hinged panels at the rear of the hull. The engine is mounted on a subframe that slides out on rails. The procedure: disconnect fuel lines, electrical connections, cooling lines, and exhaust. Remove the transmission connection. Attach hoist to engine lifting eyes. Slide engine rearward on rails until it clears the hull. Lower to ground. Reverse procedure for installation. With a practiced crew and a suitable hoist, a truck-mounted crane or an A-frame, time required, approximately 4 to 6 hours. Panzer IV crew. The Maybach HL 120 is mounted longitudinally in the engine compartment. Access requires removing multiple hull panels. The engine is not on a slide-out subframe. It must be lifted vertically out of the compartment after disconnecting all ancillary systems. The transmission, mounted in the front of the hull, remains in place. But the engine-to-transmission connection must be carefully aligned during reinstallation. With a practiced crew and proper lifting equipment, time required, approximately 8 to 12 hours. However, and this is critical, the procedure requires specialized tools and precision alignment. If performed incorrectly, the transmission can be damaged during engine installation. The American report notes, engine replacement on the Panzer IV requires significantly more time and care than on the Sherman. The German design prioritizes packaging efficiency over maintenance accessibility. Task 4. Transmission repair. Both vehicles suffer transmission failures, a common occurrence in tanks subjected to hard use. Sherman. The transmission is mounted in the front of the hull, directly behind the final drives. Access is through a large hatch in the glacis. The transmission can be removed without removing the engine. Repair or replacement can be performed by a maintenance platoon with standard tools. Time for removal and replacement, approximately 6 to 8 hours for a field maintenance unit, Panzer IV. The transmission is also mounted in the front hull, but the design is more complex. The SSG-77 Synchromesh transmission is a precision unit requiring careful handling. Field repair of internal components is difficult. Replacement is the preferred solution. However, transmission removal requires partial engine disassembly and precise realignment during installation. Time for removal and replacement, 12 to 16 hours, requiring specialized training. Major Thompson's conclusion is blunt. The Panzer IV is mechanically superior in terms of ride quality, shifting smoothness, and overall refinement. However, every major maintenance task requires more time, more specialized tools, and more training than the equivalent task on the Sherman. In a sustained campaign, this is a decisive disadvantage. But the most revealing test has not yet been conducted. December 1943. Aberdeen Proving Ground initiates an endurance trial. Both tanks will be driven until catastrophic failure. No maintenance beyond adding fuel, oil, and coolant. The goal is to determine mechanical reliability under sustained operation. The test course simulates combat conditions: 50% paved roads, 30% rough trails, 20% cross-country over broken terrain. Each vehicle operates 8 hours per day, 6 days per week. Speed varies between 15 and 35 kilometers per hour. The Sherman runs for 218 hours before the engine seizes. Total distance, approximately 3,200 kilometers, roughly 2,000 miles. The failure is traced to oil starvation caused by a failed oil pump, a common failure mode for the Continental R975, but one that can be repaired in the field by replacing the pump. The Panzer IV runs for 142 hours before multiple failures cascade. Total distance, approximately 2,100 kilometers, roughly 1,300 miles. The initial failure is a broken torsion bar. The damaged suspension causes uneven track wear. The track begins to break links. Damaged track increases strain on the drive sprocket. The drive sprocket teeth begin to wear prematurely. Increased mechanical resistance loads the transmission. The transmission begins overheating. Overheating transmission damages internal seals. Oil leaks into the final drives. The test is halted when the vehicle becomes immobile. Major Thompson's report. The Panzer IV's failure was not due to a single weak component, but to a cascade of interconnected failures. The vehicle's mechanical complexity means that a single failure can propagate through multiple systems. The Sherman's simpler design compartmentalizes failures more effectively. The Americans learn something profound from these tests. Mechanical sophistication is not the same as mechanical reliability. The Panzer IV is more refined, but the Sherman is more robust, and in war, robustness matters more than refinement. Preparing and narrating this type of story took us long efforts and hard work. So if you are enjoying the story, please consider subscribing to our channel. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. January 1944. The evaluation reports reach the War Department. General Dwight Eisenhower, preparing for the Normandy invasion, reads the findings with particular interest. His chief concern is not tactical superiority in individual tank versus tank engagements. His concern is operational endurance. Can his armoured divisions sustain offensive operations across hundreds of miles of European roads and fields? The Aberdeen reports give him confidence, not because the Sherman is better than the Panzer IV in direct combat, it is not, but because the Sherman can keep moving, and a tank that keeps moving is more valuable than a tank that shoots better but breaks down. The statistics become clearer when examined from an operational perspective rather than a tactical one. Consider the operational life of a tank, not the duration of a single battle, but the cumulative service across an entire campaign. From Normandy to the Rhine is approximately 800 kilometers, about 500 miles. But tanks do not move in straight lines. They maneuver, they reposition, they withdraw and advance. A tank participating in the campaign from June 1944 to May 1945 might travel 3,000 to 4,000 kilometers, 2,000 to 2,500 miles. For the Sherman, this is achievable. With regular maintenance, oil changes every 500 kilometers, track adjustments, minor repairs, a Sherman can sustain this operational tempo. For the Panzer IV, it is marginal, the mechanical. Complexity and the maintenance challenges mean that fewer Panzer IVs complete the full distance without major repairs requiring depot-level maintenance or component replacement. But the real killer is not mechanical reliability alone. It is the supply chain. Germany's industrial capacity by 1944 is under devastating air attack. Factories are bombed, rail lines are interdicted, spare parts production is disrupted. Even when parts are manufactured, transporting them to frontline units becomes increasingly difficult. A Panzer IV breaks a torsion bar. The replacement must be ordered. It must be manufactured at a factory in Germany, assuming that factory has not been bombed and assuming raw materials are available. It must be transported by rail to a forward depot, assuming the rail line has not been cut by Allied air interdiction. It must then be moved by truck to the division maintenance area, assuming fuel is available for the truck. Finally, it must reach the battalion workshop where the repair will be performed. Estimated time from breakdown to repair, assuming everything goes correctly, 2 to 3 weeks. In reality, often much longer, or never. Meanwhile, that Panzer IV sits immobile. It may be technically superior to the Sherman it was facing, but it is not fighting. It is waiting for a torsion bar. The Americans face the same challenges, but they solve them differently. A Sherman throws a track. The crew repairs it in under 30 minutes using onboard spares and basic tools. A Sherman breaks a road wheel. Replacement takes under 20 minutes because the wheel design is simple and accessible. A Sherman suffers engine failure. The maintenance platoon swaps in a replacement engine in 6 hours, using an engine pulled from a knocked-out Sherman recovered from the battlefield. The American approach is not sophisticated. It is pragmatic, designed for replaceability, designed for field repair, designed so that damaged vehicles can be cannibalized too, keep other vehicles running, accept slightly lower performance in exchange for dramatically higher availability. The numbers tell the story. United States tank production, 1942 to 1945. M4 Sherman, all variants, approximately 49,234. Germany tank production, 1942 to 1945. Panzer IV, all variants, approximately 8,553. The Americans built nearly 6 times as many Shermans as Germany built Panzer IVs, but that is only part of the story. Of those 49,000 Shermans, a significant percentage that were knocked out or damaged were recovered, repaired, and returned to service. American tank recovery and repair units were highly effective. A Sherman disabled by mechanical failure could often be repaired and returned to action within days. A Sherman knocked out by enemy fire if the hull was intact, could be rebuilt using salvaged components from other, damaged vehicles. The Americans established forward maintenance facilities, mobile workshops equipped with machine tools, welding equipment, spare parts. A division could perform depot-level repairs without sending vehicles back to rear area facilities. The Germans attempted similar systems, but the complexity of their vehicles worked against them. Repairing a Panzer IV's intricate transmission required specialized knowledge and precision tools. Repairing a Sherman's transmission required a good mechanic and standard wrenches. France, summer 1944. The operational reality of these design philosophies becomes evident. The 4th Armoured Division, part of General George Patton's Third Army, advances from Normandy toward the German border. From August to December 1944, the division covers approximately 800 kilometers of operational movement. Fighting, maneuvering, repositioning, the division begins the campaign with approximately 260 Shermans. By December, 93 have been knocked out by enemy action and declared total losses. Another 174 have suffered mechanical failures requiring significant repair, but the division still fields approximately 240 operational tanks. How? Replacements arrive from rear depots. Damaged vehicles are repaired in forward maintenance areas. Knocked-out Shermans are recovered and cannibalized for parts. The German 5th Panzer Army, defending against this advance, begins with approximately 190 Panzer IVs. By December, 67 have been knocked out by enemy action. Another 84 are immobilized by mechanical failures or lack of spare parts. The 5th Panzer Army can field approximately 39 operational Panzer IVs, less than 20% of their starting strength. Replacements are scarce. Spare parts are critically short. Damaged vehicles cannot be recovered because fuel for recovery vehicles is unavailable. This is not a story of German incompetence or American genius. This is a story of design, philosophy, and its consequences. The Germans designed the Panzer IV to be an excellent tank. The Americans designed the Sherman to be an adequate tank that could be built, maintained, and sustained in enormous numbers. In a war of attrition, adequacy sustained beats excellence unsustained. But the story is not quite so simple. The Panzer IV had one more challenge to face, not from enemy tanks, but from its own military's demands. 1944. The Wehrmacht is retreating on all fronts. Panzer divisions are constantly repositioning, fighting, delaying actions, withdrawing to new defensive lines. The operational tempo is brutal. A typical Panzer IV in this period might be required to move 50 kilometers in a single night to reach a new defensive position. Fight for 6 to 8 hours the following day. Withdraw another 30 kilometers that night. Repeat. The mechanical strain is enormous. Tracks wear out. Engines overheat. Transmissions suffer from constant shifting between forward and reverse. Suspensions are damaged by high-speed movement over poor roads, and there is never enough time for proper maintenance. Change the oil? There is no time. The unit is moving in 2 hours. Adjust the track tension? Maybe tomorrow. If tomorrow comes, replace that worn final drive seal before it fails catastrophically. We will deal with it when it breaks. German war diaries from this period are filled with laconic entries. Panzer IV number 412, mechanical failure, torsion bar, abandoned. Panzer IV number 533, engine seizure, crew transferred to another vehicle. Panzer IV number 604, transmission failure, destroyed by crew to prevent capture. The Panzer IV was not designed for this kind of abuse. No tank was, but the Sherman proved more tolerant of it. The Sherman's simpler systems, its more accessible maintenance points, its greater interchangeability of parts meant that even under extreme operational stress, more Shermans remained operational. A brutally simple example. Both the Panzer IV and the Sherman suffer track wear. Tracks must be replaced periodically. A Sherman crew can replace a full track in approximately 2 hours with the tools carried on board the vehicle. A Panzer IV crew requires approximately 4 hours, and specialized tools not always available in forward areas. In a high-tempo operation where every hour matters, that difference is decisive. The tank that can fix itself faster stays in the fight longer. Lorraine, France, winter 1944–45. The Wehrmacht makes its final major offensive in the west, the Battle of the Bulge. The attack begins December 16, 1944. German forces, including substantial numbers of Panzer IVs, strike through the Ardennes forest, hoping to reach Antwerp and split the Allied armies. The offensive depends on speed and surprise. It achieves both, initially. But within days, the mechanical reality reasserts itself. German armoured spearheads outrun their supply lines. Fuel is critically short. The Panzer IVs are fuel-hungry, consuming approximately 210 litres per 100 kilometres under combat conditions. American Shermans consume approximately 220 litres per 100 kilometres, slightly worse. But the Americans have fuel, Germany does not. Panzer IVs begin running out of fuel within 50 kilometres of their start lines. Crews siphon fuel from disabled vehicles to keep a few tanks moving. Priority goes to the heavier Panthers and Tigers, which are even more fuel-hungry. The Panzer IVs are increasingly abandoned, not because they are destroyed, but because there is no fuel to move them and no way to recover them. By January 1945, when the Bulge is finally reduced, the Germans have lost approximately 600 tanks and assault guns. Approximately half are lost to enemy action. The other half are abandoned due to fuel shortages or mechanical failures that cannot be repaired in time. The Americans lose approximately 730 tanks during the same battle, but within weeks, most of the damaged vehicles are recovered and repaired. The knocked-out hulls are stripped for parts. The American armoured strength recovers quickly. The German losses are permanent. This is the essence of the Panzer IV versus Sherman comparison. In a single engagement, the Panzer IV often held tactical advantages. Better gun, sometimes better armour depending on the specific variants being compared, excellent optics. But war is not a single engagement. War is 1,000 engagements across 1,000 miles. War is maintenance and supply and repair and replacement. War is which tank is still running after 4,000 miles. And by that measure, the Sherman was the superior weapon, not because it was a better tank in the technical sense, but because it was a better tool for winning a war. The Germans understood this, eventually. Post-war interviews with German tank commanders reveal a grudging respect for American operational logistics. Generaloberst Heinz Guderian, Inspector General of Panzer Troops, stated after the war, "The American Sherman was not a better tank than our Panzer IV, but the Americans always had more Shermans, and their Shermans were always running. Our Panzer IVs, when they ran, were excellent, but too often they did not run." Oberst Hans von Luck, who commanded panzer units in France, noted, "We could destroy 3 or 4 Shermans for every Panzer IV we lost. But the next day, the Americans had 3 or 4 more Shermans. We did not have another Panzer IV." The cold arithmetic of industrial warfare. Germany produced 8,553 Panzer IVs during the entire war. Peak production, 300 units per month in 1944. The United States produced 49,000 Shermans. Peak production, over 2,000 units per month in 1943. Even if every Panzer IV knocked out 5 Shermans, and many did, the Americans could afford the loss. Germany could not. But beyond the raw numbers lay the maintenance burden. Every Panzer IV that broke down removed a tank from the battle. Every Sherman that broke down could often be repaired quickly and returned to action. The Americans designed for this. Modular components, interchangeable parts, simple repair procedures. The Sherman's transmission, for example, used commercial truck components. Parts were readily available. Mechanics familiar with civilian trucks could work on Sherman transmissions without extensive specialized training. The Panzer IV's SSG-77 transmission was a custom-designed precision unit, Repair required factory-trained technicians and specialized tools. In a sustained campaign, that difference multiplied across hundreds of vehicles meant that American armored divisions maintained higher operational readiness than German divisions, even when both sides suffered similar rates of mechanical failure. The Aberdeen Proving Ground tests quantified this. A Sherman with a mechanical failure could be repaired and returned to service in an average of 4.2 days. A Panzer IV with a mechanical failure required an average of 11.6 days to repair, assuming parts were available. In Germany's deteriorating supply situation, the actual time was often much longer, or indefinite. By April 1945, the Third Reich is collapsing. Allied armies are deep into Germany. The Wehrmacht is disintegrating. Thousands of German AFVs, armoured fighting vehicles, are abandoned intact or with minor damage simply because there is no fuel to move them and no parts to repair them. American intelligence teams moving through captured German territory catalogue the finds. Panzer IV number 721, abandoned near Kassel. Mechanical condition, requires new engine mounts and transmission seal. Could be repaired in 2 days with proper parts. Why abandoned? No parts available. Panzer IV number 934, abandoned near Fulda. Mechanical condition, broken torsion bar on road wheel 3. Could be repaired in 4 hours with replacement bar. Why abandoned? No replacement bars in supply system for past 6 weeks. Panzer IV number 1057, abandoned near the Rhine. Mechanical condition, excellent. Why abandoned? No fuel. The nearby fuel dump was bombed by Allied aircraft, no alternate supply available. This is how the Panzer IV's war ended. Not in dramatic tank battles, though there were many, but in quiet abandonment beside roads throughout Germany. Excellent machines rendered useless by a supply and maintenance system that could not sustain them. The Sherman, less excellent but more sustainable, continued rolling. The philosophical question remains, was the Panzer IV a failure? By purely technical standards, no. It was an effective combat vehicle. It knocked out thousands of Allied tanks. It gave German crews a fighting chance against numerically superior opponents. But by operational standards, the standards that actually matter in war, the Panzer IV was less successful than it could have been, not because the design was bad, but because the design priorities were wrong for the kind of war Germany was fighting. Germany needed tanks that could be built quickly, maintained easily, and sustained logistically across vast distances. Instead, Germany built tanks that prioritized combat performance over operational sustainability. The Panzer IV was better than the Sherman at fighting, but the Sherman was better than the Panzer IV at enabling an army to keep fighting, and that was the contest that mattered. The story of the Panzer IV and the Sherman is not a story about which tank was better. It is a story about what better means in the context of modern industrial warfare. Is better defined by gun penetration and armor thickness, or by operational availability and ease of maintenance? The answer depends on what you are trying to accomplish. If you are trying to win a single tank duel, the Panzer IV holds advantages. If you are trying to win a campaign across 4,000 miles, the Sherman holds decisive advantages. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.